Okay, very good morning to all of you. I think my voice is audible. I'm sharing the QR code. Kindly give the attendance first, and then we will start. Okay, your midterm exam is on 22nd of June. So it's a request to all of you that you kindly go and check LMS portal that midterm exam 1 EC 605N is flashing or not. Okay, if it's not flashing on your dashboard, that means you are not enrolled. So just make sure that you are enrolled in the subject and that midterm 1 is flashing in your dashboard. Okay, and if you're not enrolled, if it's not flashing in your dashboard, then do let me know by today, because on the day of exam I'm not going to entertain all these things. Okay, inform your friends also, because every day 12 people join my class, not more than that, is in spite of 38 students. So inform your other friends. If they are not enrolled uh, on the day of exam, I will not help them out. Today by today, they should inform me if they have any problem. Okay, so give your attendance. Okay, so I was discussing with you one problem in my previous class, as far as I remember. The problem you wrote in your copy, the problem you have now in your copy. Hello, the problem you have in your copy. Respond. Hello.
Yes, ma'am.
Yeah, the capacitance of 250 picofarad, that one problem, right? So have you done that problem? Tell me the answer. Tell me the answer of self capacitance. What is the value of self capacitance? Have you done the problem? First of you tell me. Hello. Hello.
No, ma'am.
No. So tell me the question first. Any one of you, Pooja, repeat the question, please.
Capacitance of 250 picofarad
Then
produces resonance with a coil at a frequency of 4 kilo
no, not 4
hertz.
kilo. 2 by pi multiplied by 16 to the power 6 hertz. Okay, this is the frequency. Then
While at second harmonic of this frequency, resonance is produced by a capacitance of 50 picofarad.
Okay, then calculate.
Calculate self capacitance and inductance of the coil.
Okay, so this is the question which I have given you in the previous class. So two things we need to know. First of all, we need to know what is the capacitance of a variable capacitor. So let us consider C be the capacitance. Do the problem, okay? Capacitance of variable capacitor and CD is the self capacitance of the coil. Okay, and L inductance. Okay, so what is the formula of L at resonance? At resonance, what can I write? L is equals to 1 pi 4 pi square F square C plus CD. So this derivations already I have done in the previous class. Okay, I have taken the help of that equation. So here you know what is F, right? So L is equal to 1 divided by 4 pi square. What is your F? F is 2 by pi. 2 by pi whole square into 10 to the power 12. Okay. And what is your C? What is your capacitance? 250. Just now Pooja told 250 microfarad. Sorry, picofarad. Plus CD you don't know. Okay. Multiplied by 10 to the power minus 12. Now, here after solving, you will get 1 by 16, 250 plus CD. This is my equation 1. Now, you have two capacitance in your problem. Just check it out. One is 250, one is 50. Now, I have, that is for second harmonic. So, for second harmonic, I have to again write the equation for inductance. Okay. So, again, L is equals to 1 by 4 pi square multiplied by 4 by pi, because second harmonic. Okay, so I'm writing 4 by pi whole square multiplied by 10 to the power 12 in bracket take 50 plus CD multiply by 10 to the power minus 12 and take here the here it will come somehow 64 and here 50 plus CD. So here from here you got two equations. Okay, so simply you will now equate from equation 1 and 2. What you will get? One is 16, 250 plus CD. Another is 64, 50 plus CD. This is the two equation. You have to solve it. And if you solve it, you will get CD. Tell me the value of CD. Tell me the value of CD. What is the value of CD? Do the calculation. Done. Value of CD. What is this? Hello.
16.6.
Okay, 16.6 picofarad. Okay. Then from equation 1, now you know CD, right? So from equation 1, we can write L inductance is 1 by 16, 250 plus CD. So put the value of CD here, 1 by 16, 250 plus 16.6. Now Henry, tell me the answer, solve it and tell me the answer. Done? Tell me the answer. What is the answer? What is the answer of inductance? Hello?
2.34 into 10 to the power minus 4.
We will take it to 34 microhenry. Okay, this is my answer. Okay, now this problem is done. So if question comes, it will based on this particular formula. Which formula? This one formula. This is important formula. Okay, 1 by 4 pi square f square. This formula. Okay, we can go to the next topic of this chapter. That is, we are done with the resonance method and measurement of inductance. Okay, so today we will start with measurement of capacitance. Okay. Okay. So in high frequency measurement, how we do the measurement of capacitance? Now see, substitution method is normally used for measurement of capacitance at high frequency. Okay. So a picture I will show you. So the picture is like this, very simple picture. This is a very simple picture. So if you have your pen and copy, you can draw it. Okay. Because these pictures you will require. Okay. So this kind of structure, this is a substitution method. I mean, here you will be having an oscillator. Okay. And here will be having output coil. Okay. And here's the inductance L. This is a switch S. This is a capacitor C. This is a capacitor, you can say standard variable capacitor CS. And this is TVM or VTVM, with you can say whatever we have say, VTM or TVM. Voltmeter. Now, you see here, this is the substitution method. Substitution method. Measurement of capacitance. Okay. Measurement of capacitance by this substitution method. This is the picture. This is a simple circuit for measurement of capacitance C. Which capacitance we have to measure? This one. This C is unknown to us. Okay. And this C is connected in parallel with a variable capacitor, that is this one. This is a standard and variable also. So standard capacitance is of the same order as the unknown capacitance. Okay. So now what happens? With the switch S, when it's open, the resonance is obtained by varying the standard capacitance CS. Okay. So remember one thing, when switch is on or switch is open, you can say more appropriate word. When S is open, S means my switch is open, that what happened? Resonance is obtained. Okay. Resonance is obtained across what? Across by varying the resonance is obtained by varying the standard capacitor, standard variable capacitor, that is CS. So the resonance condition here is indicated in this particular meter, that is VTVM or TVM, which is connected across the standard capacitor. So let you just now consider, let F be the frequency, F be the frequency in hertz. Okay. L be inductance of the coil, that is coupled the output of the oscillator. So L is inductance, and inductance we denoted it as H. Okay. And C, you can write as CS, that is a setting of standard capacitor with switch when open, or you can write it as CS1. Okay, because CS we are considering standard capacitor. So CS1 is the standard capacitor or setting of standard capacitor, you can say. The setting of standard capacitor, that is CS, when switch is open, when S is open. Okay. And so it can be written as farad F. So from this particular three terms, F, L, C1, we can write that is CS1, that is my setting of the standard capacitor, that can be written as 1/4 pi square F square L. So there is a very important formula, this formula, that is, this is the setting of the standard capacitor when the switch is open. So formula we can write CS1 equal to 1/4 pi square F square L. Now this is all about when S is open, that is when switch is open. Okay, when switch is open. Now let us move to when switch is closed. Now come to when switch is closed. What happened when switch is closed? When switch is closed, the unknown capacitance, it is connected parallel to the standard capacitor. This is the picture. This is the unknown capacitance, this is standard capacitor. So both are connected parallel to each other. Now keeping the frequency F the same as the previous, when switch is open, that part, frequency is same. The resonance conditions here is again obtained by varying the standard capacitor. Okay, so if that thing happened here, when switch is closed, my CS2 I will take, that is obviously setting of the standard capacitor when my switch is closed. Okay, so this is setting of the standard capacitor when with switch closed. Okay, switch closed. Now if this happens, then we can say that in this particular picture, we get here what? We get here C plus CS2. C is my unknown capacitance. CS2 is my setting of standard capacitor with the switch closed. That will be equal to 1 by 4 pi square F square L. So this is my equation 2. Okay. So previously I had that equation, that was equation 1. This was equation 1 with switch open. And this is equation 2. Now, solving these two equations, the value of this 1 and 2, we can get the value of unknown capacitance. So what is that? Value of unknown capacitance. Okay, so that can be written as C equals to CS1 minus CS2. And this we are getting from equation 1 and equation 2. So we are getting this kind of equation, equation 3. So thus the value of the unknown capacitance can be directly known from the difference of the two settings of the standard capacitor. Okay, one when his switch is open and one when his switch is closed. So this is the method how we can find the value of capacitance at high frequency. Okay, so this is the one process, and this is all about measurement of capacitance. Now let us move on to the next process, that is measurement of effective resistance. Under that you will be having two methods, effective resistance. Okay. Wait, we can also do a problem. After that, we can move into, actually not required. Let us do the equations first, then we will do the problem. Okay. So now I told you that measurement of effective resistance. Now, under measurement of effective resistance, you will be having two methods. One is resistance variation method, another is reactance variation method. Okay, so both will be having their own formulas, and that we have to check once, and it has some derivations also. Okay, so let us start. I'm moving to the next page. Measurement of effective resistance. Okay. So check it out, this method. There are two methods of measurement of effective resistance of a series RLC circuit. Okay. What are the two methods? First method comes resistance variation method. And second method is reactance variation method. Okay. So in resistance variation method, what will happen? Let us discuss the first method, that is in first method, suppose the effective series resistance of a resonance circuit, here it will be measured. by adding extra resistance from outside. Okay, so here also you have to draw picture, very easy picture. Similarly, all the picture you will be having, I mean, a similar pattern you will see. First of all, they will be having an oscillator. Okay, and then with the oscillator here, you have to connect the output coil. Okay, so this kind of coil is there, and here you will be having another coil, and with this here a resistance and a capacitor here connected. Okay, and then you will be having a meter, that is VTM or TVM, whatever. Okay, so this is my oscillator, this is my oscillator, and here you again, here you have to connect a VTM in this case, and here you will be also having an ammeter in this particular area. Okay, here you will be having an ammeter. So let us, this is the output coil. This is the output coil. I'm writing here. Output coil. This is my ammeter. This is my ammeter. And this is my TVM or VTM, VTVM or TVM, whatever you call it. And this is my L. This is my R. This is my C, which is variable. And this is a voltage you will get across this capacitor. And this is VTVM or TVM. Okay, so this is the picture, and the current will be flowing through it, so we can call it as I current is flowing. And now a diagram we have to draw also on the basis of this plotting of XY axis. Okay, so that diagram I'm doing on the next page. So this picture has been understood now, this picture. So every picture in case of frequency, in case of measurement of any parameter at high frequency, having this similar pattern of picture. Okay, oscillator, then output coil, then inductance, resistance, whatever we need to at that case. Okay, now let us move on to the next page. I need to draw a picture, so let me do that for you. So here you will be having, this is my y-axis, this is my x-axis. Okay, and another thing you have to draw here, this is the thing, and here you have to extend it to some point like this. Oh, no, sorry. So like this, you have to draw it, you have to extend it, and this is your R. Okay, this is everything I will discuss. Okay, this is R1. R1 is additional resistance that is inserted. This area is 1 by V, and this is a point O, and this is, you know, a O dash point. So let us discuss first here what things are required. First of all, you will see here whatever equation we are writing from for the resonance at resonance. So here we need to know what is E. E is the induced EMF, because in the equation what we will get at resonance, that will be your E upon, I mean, E is, you can also say EMF induced in the resonance circuit. I0, let me first tell you that formula. I0 equal to E by R plus R1. This is my formula which I can write at resonance. Okay, this is at resonance. Now the question comes, what does each parameter is known as? First of all, E. E is the what? E is the EMF induced in resonance circuit. What is I0? I0 is the current in resonance circuit. What is R? R is the effective resistance of resonance circuit. Okay, and R1 is the additional resistance which is included. Okay, this is the added resistance which is inserted in the resonance circuit. And L, you all know, L is the inductance, C is the capacitance, V is the reading if in time comes, V is the reading of the voltmeter connected, and this we will require actually. Okay, across the voltmeter connected across C, and another will be F0. F0 is the resonant frequency. Okay, resonant frequency. Now here in this particular case, resonant frequency, you know. So at resonant, I told you this formula. Just let us take as equation 1. Now what is the voltage equation we will get from here? Voltage equation. That will be V equals to I0 by 2 pi F0C. Okay. So now from this particular equation, you know what is F0. F0 is resonant frequency. Okay. So I0 you know. So you put the value of I0 from equation 1 into this equation 2. So if I put the value, then what it will come? E by R plus R1, okay, 2 pi F0C, this kind of equation will come, this equation 3, or, sorry, not equation 3, don't keep it. we can find out R plus R1 from this picture. That will be definitely E divided by 2 pi F0 CV. Okay. So I think you understood this equation up to this much equation. So I can write it as equation 3. Now, if the values of E, F0 and C, what is E? Is the EMF induced. It is the EMF induced in the resonance circuit. So if the EMF induced resonant frequency and capacitor is kept constant, then what we can get? What we can get? So we are keeping this. What we will do in the next stage, we will make this whole thing constant. See, from this equation, this portion we will make constant. Okay, so let us move to the next page. So now, if I say, if the values of E, F0 and C are constant, then what will the equation will become? R plus R1, and that will portion E upon 2 pi F0, that we now will consider as K. So remember here, this constant we will take it as K. Okay, K. So moving to the next page, we can write this equation as K divided by V. So this is my another equation, maybe equation 4. Okay, so previous equation was 3. Now it's equation 4. So where K is constant. Okay, K is constant and K is somehow E by 2 pi F0C. So thus under this above condition, if we plot any curve, that will be how it will look. How it will look, the curve which I have plotted. Let me go to the previous page. This curve I haven't discussed. Look into this curve very nicely. What I have plotted only that thing. This formula I have plotted. Check it out. R plus R1 is equal to, you can take it as K by V. So K is a constant, right? Constant we can't plot. So we can plot 1 by V. So 1 by V I have plotted along the y-axis, and R plus R1 I have plotted along the x-axis. Now, clear? So this is, so depending upon the formula which I got, I have plotted a curve between 1 by V and R1, and we get a straight line as shown in this particular curve. Now, effective resistance, if you say, it is given by this O dash and O. This is my O dash and this is also, this is my effective resistance. Okay. And it provided that the loss resistance of capacitor resistance, some at point of time calculation, we neglected. So from the above analysis, whatever we have done, we have find out the voltage, the resistance and all. We come to the conclusion that we can determine the effective resistance with this process by inserting an extra resistance R1. Okay. And then second is, analysis is only valid if the induced EMF is made constant. Okay. So let me go to the next page and tell you. So what are the conclusions we can get? Conclusions from this particular one is, if we add R1, we can proceed with this process. Okay. Second is, EMF need to be constant, which we did here. Okay. Then only we can, this analysis is valid. And third is, definitely we have to also check whatever output we are getting on the VTM and TVM. That is also important. Okay. So so measurement of the previous diagram which I showed you, That was measurement of, this is measurement of effective resistance by resistance variation method. Okay. Second, we will now move on to, so these are the conclusions or inferences we can derive from this method particularly. Now our second method is reactance variation method. Okay. Now in reactance variation method, let me tell you, I'm doing it here only. Leave it. Let us go to the next page. Second is reactance variation method. Okay. So in reactance variation method, what is happening? Same picture you have to take it. One oscillator you will be having. Okay, with the oscillator, connect the output coil. And again, you can connect your inductance L. With that, you need an ammeter here. And you have a capacitor here. Just a very simple picture. Okay, this is my oscillator. This is my oscillator. And this is my output coil. This is my L. So this is the picture or measurement of effective resistance with reactance variation method. Now in this method, how we can do it? A thermal ammeter. This is the thermal ammeter. Okay. A thermal ammeter here is connected to measure the value of the current flowing, this thermal ammeter. And circuit reactance is varied by varying this capacitance C or the frequency. The reactance adjusted till the ammeter reaches the maximum value. Okay, and this happens definitely at resonance conditions. So maximum value of the current from this picture, we can write maximum value of current. We can write I0 equals to E by R. I0 is what? Current at resonant condition. E, you know, EMF induced. R is the effective value of the resistance. Okay. So the reactance, then we have to adjust. So reactance can be adjusted in such a way so that the actual current which is flowing through it, that becomes, you know, divided by √2. That is reactance is adjusted. So after adjusting, the current that we will get, that is equal to I0 by √2. So if I get this value, then I can write I0, I know already E. Okay. And down I will try to put here? I will put here R square plus X square. Okay. So this is equal to your I0 by √2. And this we can write as E by √2R. So this R square, this is, we can write as √2R. Okay, so X we can write somehow in terms of plus minus R. So two values of reactance which give a current. What current we are getting? Simple, I equal to I0 by √2. So this equation is important, that what current we are getting here by adjusting the reactance. Now difference of this two values of reactance gives, more effective resistance, means less current what we are getting, that is I0 by √2, but the effective resistance we will get, that is something double. Okay, so this is the actual proportion of how we are getting. Now this method I need to speak with you more elaborately, that I will do in the next class. So apart from this reactance variation method, previous method which we discussed just now, that is the resistance one, was that comfortable? I mean, did you get this method, understood this method? Very easy, nothing much, only you have to follow some steps. Okay, so today we have, yes.
Ma'am,
Yes.
how is thermal ammeter different from normal ammeter?
Thermal ammeter detects the temperature also. Okay, normal ammeter, they are not that much susceptible to temperature, but thermal ammeter, if we require, it give us current in addition with the temperature also. Okay, that is why we tell it as thermal ammeter. So everywhere we don't use thermal ammeter. Okay, generally we don't use. These are expensive devices. Where we require, there we actually use it. Okay, thermal ammeter is basically it gives
So
us
it is ammeter, ma'am. So it is ammeter plus thermometer.
not exact thermometer. There is a if you see thermal ammeter, if you see that kit, that device, you will see there is a section where temperature is detected. Thermometer directly we can't say, but yes, it is susceptible to temperature. If you want to understand that the device which is connected to ammeter, how much temperature is flowing through that, you can detect. Okay, you can detect. That is a thermal ammeter. So there is a section to get the temperature. Yes. Bolo.
Then why we need thermal ammeter in reactance variation method?
Reactance
in,
variation method, yes, we need thermal ammeter because here we are varying the reactance. Because see, our motto is to find the effective resistance. Which method? Reactance variation method. Now, in this reactance variation method, there are some parameters, C and capacitance and frequency. We are not here adding any extra device. Okay, what is there in the circuit? Inductance, capacitance, and frequency. So due to this reactance, I mean, what parameter we are taking, that is why we are using thermal ammeter here. So it's used to measure the value of the current flowing. Okay. So specifically in reactance variation method, we are using this ammeter. Now, why? Because to measure the current. That's it. And in depth, if you ask me, then I have to study more on this method. Okay, because it's not even written in the book also. Okay.